So section B, I have shared one video file. Let me show you first your files folder. I just want to know that how many of you have watched that video. 2-hour recorded lecture. With the title So this movie, Design of Beams. Tuesday I have uploaded this video on your Teams folder. So have you watched that? As in your case, last time I stopped at a slide where we discussed. We stopped at this slide of application of row equation to design the beams. So have you watched your own lecture recorded with your section on April 22nd, 2-hour lecture? Anyone who has seen that video recorded, sorry, on 28th April, and then on Tuesday I uploaded design of beams 2 hours lecture. So please raise your hand, those who are thinking that they have the full command on those recorded video lectures. Now they can handle the design problem. आप लोग किस गलतफहमी में है कि ये सब्जेक्ट ऐसे ही क्लियर हो जाएगा? So not even a single student has followed the recorded video, last lecture or the latest uploaded on Tuesday.
सर वो रिकॉर्डेड जो पहले वाला लेक्चर था वो देखे थे, लेकिन वो ट्यूसडे वाले का पता नहीं था कि अपलोड हो गया होगा, इस वजह से।
जो लास्ट लेक्चर है वो आपने उसको रिपीट किया है घर पे?
यस सर, उसकी रिकॉर्डिंग देखी थी।
Okay, so I think the latest uploaded on Tuesday 2-hour lecture, please watch that video as well. It is part of your coursework. Today, since we have 1 hour commitment, 1 hour interaction, so I will try to finish as maximum slides as possible, but the complete design problem with the discussion on remaining slides is present in 2-hour lecture, Design of Beams video lecture. So please watch that video as well. Although I will repeat what I have recorded in that video again, but I believe that advantage of lecture will be when you people will follow the recording, or at least you attempt at home those problems which I have solved during online lecture. So then I will assign you some problems on rectangular beams. So you need to solve them, analysis and design problems, and then that will help you to attempt questions in exam. So I will cover today's lecture with the suggestion that although I will repeat all those slides which already I have recorded and uploaded, but just for your interest I can repeat them again, and also I will record today's lecture so that if you are interested you can watch this video as well. But one thing I can tell you that this subject you can only clear or can earn good grades if you will be following the topics right after the lecture. If you are not repeating the lectures, you are not attempting the problems at your own, then you can't earn good grades. So this subject is little lengthy but very much interesting and applied. So let me start the recording of 1 hour lecture, and what I am going to discuss here, its recording is also available. So in last lecture I discussed derivation of this row equation, and I also applied this equation to determine the reinforcement ratio in a cross section of one assumed problem. Now on this slide again there is a summary that how to classify that section is under reinforced or over reinforced. So I repeat that first thing is you will calculate the row of your cross section, area of steel in the cross section, and that area of steel in the cross section divided by the cross sectional area. If it is a capacity problem, you are already given with the area of steel and sectional details, so you can determine the reinforcement ratio of that cross section. Even if it is a design problem, you will calculate the row from this equation, and we are going to attempt this equation for design problem, and I have done one problem in online lecture which I have shared with you. So you will find the solution of the problem where I applied this equation to design the beam. So even if you are designing a beam, you will get rho from this equation. Once you get the rho from this equation, compare it with the rho max. Rho max, you remember that we derived this reinforcement ratio. It is equal to 0.85 beta 1 Fc prime over Fy into 3 over 8. So this reinforcement ratio is very useful because it helps us to classify the cross section, that whether it is tension controlled under reinforced or not. If rho is greater than rho max, suppose if rho is greater than rho max once you calculate, but still it is less than rho balanced, then still section is tension controlled, but it is now transition controlled. Still section will yield before crushing of concrete, but section will not give you, the steel in the section will not give you 0.005 strain or bigger when concrete will crush. So if rho comes out to be greater than rho max, but it is less than rho balanced, we are in the transition domain. But if it comes out to be greater than even row balanced, then it means we are in the over reinforced domain. Furthermore, you can also determine neutral axis depth, which is uniform stress block depth or neutral axis depth. After design, you can write the equilibrium equation and you can get A and then C. And this step I also have followed in the solved problem, which I have uploaded. So this A and having the effective depth of the cross section, you will calculate the strain in the steel bars, farthest steel layer strain from the neutral axis. And if this strain comes out to be minimum equal to or greater than 0.005, this will be another information that section is tension controlled, it is under reinforced. So both row or the neutral axis depth helps us in getting the classification. And if you have C in hand from similar triangles, you can get epsilon S and then you can compare it with 0.005 to check what is the type of cross section. However, if in design problem, I mentioned in the last lecture that when you calculate rho, there are two roots of rho. One is with plus sign and other is with minus sign. With plus sign we ignored because rho with plus sign will give us the reinforcement ratio even greater than rho balance. So we ignored that root and we selected the root which will give us rho less than rho max. In this equation, when you will be using it for design of the reinforcement ratio, if section what you are designing is resulting into over reinforced cross section, what warning you will get once you will put the value inside this square root. For example, R is actually mu over BD square. If I expand this equation, it is mu over BD square. So once you will put the values, you will get under the root negative term if section will result into over reinforced section. So that will also be one hint for you that what you are designing a cross section that will not result into a tension controlled, a desirable cross section. So be cautious. You need to change the effective depth, change the cross section in order to get the answer from this equation without getting negative sign under the root, because if negative sign will come under the root, it becomes a complex number. We are not interested in getting such number, but we are interested in getting a reinforcement ratio which is less than rho max. So this is another benefit of using this equation, that during design this will give you one information that are you getting the cross section which is ductile, under reinforced, tension controlled. In addition to that, when I want to design a cross section, I also need to fix the cross section dimensions. Design problem means that not only area of steel will be calculated, but also the width and the depth of the cross section will be decided to proportion the cross section. So design means to fix the cross section and then to calculate the area of steel. And on this slide, we are providing you one very small derivation to determine that effective depth of the cross section, which will guarantee you that the section what you are going to design will result into tension controlled under reinforced. So a minimum effective depth you will get from this simple derivation. And for design problem, to fix the cross section, you will call this equation. And for this derivation, we are using the compression force into lever arm part of equilibrium equation. So you know that T is equal to C. So either T into lever arm or C into lever arm will give us internal nominal capacity. We are using here compression force into lever arm to get the nominal capacity. And furthermore, we are multiplying this nominal with the capacity reduction factor to get internal resistance, ultimate internal resistance, capacity, ultimate capacity. And we are comparing it with demand, external applied ultimate movement. So in this way, we are equating the demand with the capacity. Now in this equation, what I will do, I will substitute phi with the tension controlled under reinforced phi. I will substitute Cc with the Whitney's uniform stress block depth equivalent force, which is 85% of Fc prime on the area, which is A into B. So uniform stress into area will give me Cc. And I'm replacing the lever arm between T and C with D minus A by 2. So this lever arm, you are well familiar with this lever arm between internal couple between T and C. Now, after this substitution, I will make one intelligent substitution that I will put A in this equation from that strain diagram, which will give me, corresponding to crushing in concrete, a steel strain of 0.005. So that unique neutral axis depth I will use, which will give me the cross section with steel at 0.005 when concrete will crush. And we have done this derivation, and it is equal to C equal to 3 by 8 D. So we have derived this equation, and I can multiply this with beta 1 to get A. So you remember that we did this derivation at, it will finish at 2 p.m. It is, you know that this derivation is with reference to the steel strain of 0.005, and we derived this equation with A is equal to beta 1C, and A was 3 by 8D into beta 1. So this A from this strain diagram, we are replacing we are substituting here, and in that replacement of A with this typical neutral axis depth, I can simplify this right hand side and I can rearrange it by keeping D on one side and bringing all other variables on the right hand side. So this equation is so powerful that while making a design, you are given with the demand. And if you decided the width of the cross section based on your support dimension, available formwork, you know the concrete strength. This equation will help you to get that minimum effective depth, which will correspond to a strain of 0.005 at failure of concrete. So it means that section is tension controlled under reinforced. If you will round up the calculated D, you will surely get in that cross section strain more than 0.005 corresponding to crushing in concrete. We will use this equation to fix the effective depth, and then in that effective depth I will add the cover. Cover I will add following the ACI guidelines, that what must be the clear cover below the steel, then the die of the ties which are enveloping the longitudinal steel, and then getting to the center of the longitudinal steel. So that cover I will also add in the effective depth to get to that gross H. If we keep in our design problem D greater than D minimum, resulting section will be tension controlled under reinforced. Now, up till now, we discussed capacity of a under reinforced cross section, design of a under reinforced cross section. Now, we want to cover a second category, which is over reinforced cross section, undesirable behavior. So there are various stages of its performance when you will incrementally load that over reinforced beam. So when beam is over reinforced and suppose it is simply supported and the mid span section is at maximum stress, and once you will put load on that beam, initially beam will be uncracked because stress at the bottom fiber will be less than modulus of rupture of concrete. So section is uncracked, stage 1. Then if you increase the load, incrementally you are putting more and more load, a stage will come that the concrete will crack because tensile stress will cross the indirect tensile strength of concrete. So these two stages are just like the section what we have studied under the tension controlled under reinforced cross section. Same stages 1 and 2. But the stage 3 in this over reinforced cross section will be that if you will put more load and now you are approaching the ultimate limit, what will happen? Concrete in extreme compression fiber will crush, but steel will be at that instant below yield. So epsilon s will be less than epsilon y, and stress below yield stress. Such section will be declared compression controlled or over reinforced, and due to this brittle behavior, because there will not be warning, because steel is still in the elastic range and there will not be offensive sag, crack opening and widening and propagation, and sudden failure will take place. So a strict reduction factor will be imposed, and that is 0.65 for such compression controlled cross sections. Now, in order to get the equation for that over reinforced cross section, and to determine that what is the capacity of that over reinforced cross section, we will write one internal capacity equation, and again using the compression force into lever arm as the internal movement resistance. Rather T into lever arm, we are using C into lever arm. And in addition, we will put phi as well. On the left hand side there is a phi, so on the right hand side there should also be phi. Phi B into CC into lever arm. Now phi B will be 0.65, and I am substituting CC with Whitney's uniform stress block depth theory based compression force CC into the lever arm between the internal couple. Now at this stage, what A I must put, because in this right hand side part of the equation, I know each and everything to determine the internal capacity of the over reinforced cross section, but I have no idea about the neutral axis depth. Had it been a ductile cross section, tension controlled, under reinforced, I could get A equal to beta 1 C, and C will be 3 over 8 D if the strain in the steel is 0.005. If I have idea at this stage that when concrete will crush, strain of the steel will be of this magnitude, then I can get A. If I, for example, if I have a clear idea when concrete will crush, steel will be at 0.001. Then corresponding to this, using similar triangles, I can get C and A value. But I have no idea that how much will be the strain in steel when concrete will crush. It is unknown. So is Fs unknown, not exact one mechanical value known to me. So what I will do, I will call basic equilibrium equation T equal to C, and I will put T as ASFS and C as 0.85 C prime AB. And I will keep A on one side and rest variables on the right hand side. This A from equation 2, I will put equation 1, and and then I can get one equation with the value ASFS over here, just put over here, and then thus this complete equation over here. But problem is, I want to know what is the A value which will give me the answer of my internal capacity of this over reinforced cross section, so that we can do with this little exercise which is explained here on this slide. What I mentioned on the previous slide, the same is drawn here. Steel strain concrete strain 0.003 and steel strain any value epsilon s, but it is below epsilon y. It may be 0.001, 0.015, any value which is less than epsilon y. So using the similar triangles and writing this equation, epsilon s divided by 0.003 and d minus c over c, and replacing c with a over beta 1 and keeping epsilon s on one side, you can derive this equation for steel strain from similar triangles, just drawing that strain diagram with steel strain at epsilon s. Now on the right hand side, A is still unknown. A or steel C is still unknown. I will multiply this epsilon s with modulus of elasticity as Hooke's law is applicable, and I can get Fs. And 200,000 megapascal multiplied with this strain will give me 600 into beta 1d minus A over A. So I suggest you to memorize either this in strain format, the epsilon s equation for over-reinforced beam, or in stress format, the equation for over-reinforced beam. And this equation is available when epsilon s is less than epsilon y. We can term it as equation 4. Now this epsilon s, over here there is Fs, right? What I am doing, I am putting in this equation, equation 2, this Fs which I have derived on this slide, that Fs is 600 into beta 1d minus A over A in this equation 2, and once I simplify this, I got the answer that this equation is a quadratic equation in terms of A. So if you simplify this equation, x and y are coefficients. Equation 5 will give you a quadratic equation of A. You will get two roots of it. One root will be positive and other will be negative. Distance can't be negative. So you will select that A, and that A then can be checked by putting in this strain equation to determine what is the epsilon s, and obviously epsilon s will come out to be less than epsilon y. That A you can also put here to determine Fs, and obviously Fs will be less than Fy. But now you will know exact mechanical value of the stress in the steel. Exact magnitude now you will know, since now you have solved the strain diagram and you know where is the neutral axis depth. Now in this capacity equation, what we have written here, which involved A and in circular brackets D minus A by 2, you can put this A and the A determined earlier and not only this, you will determine the flexure capacity by C into lever arm. Now you can also determine the internal capacity by T into lever arm, because since now you know Fs, so area steel into Fs will give you T, and from both equations you will get the same answer. So in this way, for over reinforced cross section, by using 5.65, you can get the internal capacity of a over reinforced cross section. So this is what will become important when you are analyzing a over reinforced cross section. So you get the idea from the rho value, that suppose your rho comes out to be in the given cross section greater than rho balanced. You are doing the initial classification screening and you got the idea that in your given cross section rho is greater than rho balanced. So there is a big hint for you that you are actually dealing with a over reinforced cross section. Now in order to get the capacity of that over reinforced cross section internal movement resistance, you will use this flow chart what I have explained over here, that first you will get the A value. From A you will get epsilon s and Fs, and then finally you will apply this to get the internal movement resistance by selecting 5.65. So this is the discussion on analysis or design of tension controlled under reinforced beam and analysis of over reinforced beams. New design, we will not recommend to design a over reinforced beam. But while making analysis, you may come across a beam which is over reinforced and you have to submit its capacity. Then you need to follow this flow chart to determine the capacity of over reinforced cross section. But in new design, your design will not be approved unless you will design section as tension controlled under reinforced. Now this there is a problem which at the moment it seems in this presentation that it is quite haphazardly shown in this white screen. So let me redraft the problem, but I think I will not be able to complete it because in your lecture time is limited. But as I said earlier, that with section probably A, I have completed this problem in online lecture and the video is shared with you. Let me try to solve it as maximum as possible, but rest of the video you can watch later on, and then that will help you a lot in designing the beams tension controlled under reinforced. So the problem is like, I assign you, please design a beam which is simply supported, and it is of span 6 meter. So I am just asking you a simple question, that beam is single span, simply supported, and it is subjected to a uniformly distributed load of 75 kilonewton per meter. So beam has the self weight, obviously, but we are giving you total load including self weight, and its ultimate value is provided, that ultimate uniformly distributed load on the beam including its self weight is 75 kilonewton per meter. Beam has the concrete of grade 20. It is 28 days compressive strengths of standard cured cylinders and average of 2. As per ACI, this strength will be based on testing 2 cylinders, standard cured. When I say standard cured, it means standards of size 6-inch dia, 150 millimeter dia by 300 millimeter height, at the age of 28 days, and they are cured under standard temperature. The water which is used for curing cylinders, that water temperature will be according to the ASTM specification relevant for that testing of cylinders. And at the age of 28 days, when you will crush them, average of the strength of 2 cylinders will tell you what is the compressive strength of concrete. While tension test on steel bar will tell you the steel grade, and in this problem, we want to design the beam with steel of yield strength 420 megapascal. So this is the statement given to you. And now, since it is a design problem, you actually need to proportion the cross section first, and then you need to tell how much steel bars inside must be present to resist the ultimate moment demand. And for this simply supported beam, obviously the bending moment diagram will be parabolic, and the maximum moment demand will be at mid span, and its value will be, because end conditions are simply supported, so its value will be WU L squared by 8. So please tell me how much will be the moment in kilonewton meter.
$37.5 kilonewton per meter.
जी जनाब, दोबारा बोले.
337.5.
आपकी आवाज थोड़ी सी कट जाती है, फिर बोलें.
337.5.
नहीं यार, आपकी आवाज क्लियर नहीं आ रही. मुझे एंड पे 5 नहीं देता है, शुरू के वर्ड्स सुनाई नहीं देते. एनीवन एल्स विद क्लियर वॉइस और बेटर इंटरनेट स्पीड? जी दोबारा बोलें. कमाल है यार, आपकी आवाज भी दरमियान में गायब हो जाती है. 3. Let me go to that previous calculated value. Yeah, the section A responded me 337 point, right? This one value you are asking, right? 337.5 kilonewton meter. This is a movement, ultimate maximum movement which you want to resist in the cross section. And now, as a structural engineer, you have two tasks which you need to fulfill. One is you need to fix the B and the H as well, and then tell how much steel bars must be present in the beam to resist the demand of 337.5. Now, if you recall, I mentioned in the class that serviceability requirements dictates that deflection of the beam should be within limits, and as well as crack widths at service loads. To fulfill the serviceability requirements, ACI in chapter 9 has given you one table in which H is proposed corresponding to different end conditions and also based on steel grades. And I have shared that table with you in the presentation. Please open that table in ACI chapter 9 and tell me that ACI proposing how much H span by which number to fulfill the serviceability requirements. So can you open that table in chapter 9? And in our last presentation, that chapter was shared with you, that for grade 420 steel, and if end conditions are simply supported, beam is single span, what span by number is proposed coefficient in denominator, that whether you want to keep the, for example, if I push the escape button, or let me end the show. So they ask me, want to keep your ink annotations? If I say keep, it means they are here. So let me share with you that table which I mentioned in my third or fourth lecture. And the same table is also available in, yeah, this one. So do you remember this table? So we are having this end condition simply supported, grade 420, so span by 16. It is given in chapter 9 of ACI 318 2019 publication. So you are right, span by 16. So 6,000 over 16. So how much? H. You please repeat.
Sir, 375.
Good. 375. So this deflection, this gross depth is ACI proposed, and you are advised not to go below this depth unless you have some sound calculations of deflection, and you can prove that even selecting a depth below than this can give you the deflections well within the permissible limits. But normally we keep this guideline as mandatory requirement, and we design the beam with the gross depth above this H value. And since I mentioned that in tension controlled under reinforced cross sections, which is our design objective, we need to select that effective depth which should be greater than or at least equal to, we derived this equation on previous slides, mu over 0.205 fc prime into b. So we also need to check that this equation gives us how much effective depth, and then adding the cover inside I can get the gross H. If I will violate this D minimum, I will not get tension controlled under reinforced cross section, and which is actually undesirable. I need to design a beam with D at least equal to D minimum. So I think this, from this step onward, I have discussed each and every step with section A, and the online recorded 2-hour lecture is also uploaded with the title Design of Beams. So please watch that video at your home, and also let me know before start of next lecture if you face any difficulty in understanding that recorded online lecture. And next week we will have 2-hour lecture inshallah, and then before starting the next discussion I will make sure that each one of you has seen that video and knows how to design the beam, because this is very important topic, and I recommend you to solve all the design problems in your reference book with reference to ultimate strength design, analysis and design problems. Solved ones first, try to attempt them, and then at the end of the chapter unsolved ones. So those problems will help you a lot. So I can download your attendance at the moment. Hello. Hello. Relationships are very much I would say applied one. अगर आप बहुत ही डिपेंडेंट होंगे फार्मूला शीट पे तो फिर आप यूँ समझें कि आपने कंसेप्ट उतना क्लियर नहीं किया। तो कुछ बड़ी बेसिक इक्वेशन हैं जो कि वैसे ही आपको याद होनी चाहिए। अदरवाइज यस, हम आपको कुछ अगर एग्ज़ाम में हम मिड टर्म में नॉर्मली कम इक्वेशंस हम डील करते हैं तो बाज़ औक़ात क्वेश्चन पेपर में ही डायरेक्ट वो इक्वेशंस शेयर कर ली जाती हैं या फार्मूला शीट बुक भी अलाउ कर सकते हैं।
ओके सर। सर इसमें एक और चीज़ पूछनी थी कि सर जो हम L/16 से निकाल रहे हैं उधर से हम ग्रॉस डेप्थ जो है वो लेंगे और बाकी जो डी मिनिमम है वो इफेक्टिव डेप्थ होगी हमारी कवर को एक्सक्लूड करके।
जी, इस केस में कोड आपको ग्रॉस एच रिकमेंड कर रहा है। इस बेस पे जो इक्वेशन हमने ड्राइव की है वो इफेक्टिव डेप्थ को एस्टेब्लिश कर रही है, उसमें हमें कवर ऐड करना है एंड देन दैट कवर आफ्टर एडिंग इन इफेक्टिव डेप्थ विल बी कंपेयर्ड विद दिस मिनिमम रिक्वायर्ड एच। मैं एच को ही एच से कंपेयर करूंगा, लेकिन यहाँ पर मुझे डी के अंदर उस डी के अंदर मुझे once I will calculate d minimum based on this equation, I will add cover in it, concrete cover, और ये फिर मिलकर H बनाएंगे। इन दोनों में से जो बड़ा होगा that will cover. So we will compare both and the larger will be selected. Normally जो आपकी डिफ्लेक्शन का H है वो रेयरली गवर्न करेगा। हम नॉर्मली टेंशन कंट्रोल डिज़ाइन करते हुए हमें D ज़्यादा रखना पड़ता है और उस वजह से मोस्टली आपको यही आंसर मिलेगा कि आपका डी मिनिमम की इक्वेशन कंट्रोल कर रही है। आगे हम एक डबली बीम पढ़ेंगे, वहाँ शायद आपको जो सर्विसिबिलिटी गवर्न करना शुरू कर दे और आपका डी कम आए बीम का। जो बीम अभी हम डिस्कस कर रहे हैं इसको हम कहते हैं सिंगली रीइंफोर्स्ड बीम, इसमें ये डी कंट्रोल होगा। आगे हम डिस्कस करेंगे डबली बीम के स्टील कंप्रेशन जोन में, यहाँ भी होगा। जब बीम डबली होगा कि कंक्रीट के कंप्रेशन के अंदर भी स्टील है और कंक्रीट इनसफिशिएंट है, स्टील भी कंप्रेशन फोर्स जनरेट करेगा, उसे हम डबली बीम कहते हैं। उस केस में आपका एच काफ़ी कम होगा। वो एच स्टिल इन दोनों में से जो बड़ा एच होगा दैट विल गवर, ग्रेटर विल गवर। वो अभी नेक्स्ट टॉपिक हम डिस्कस करेंगे इंशाल्लाह। ये अभी हम जो डिस्कस कर रहे हैं दैट इज सिंगली रीइंफोर्स्ड बीम। मैं कंप्रेशन साइड पे कोई बात ही नहीं करता कि वहाँ कोई स्टील है, आगे हम उसकी बात भी करेंगे कि ऊपर कंप्रेशन साइड पे भी स्टील है अबव न्यूट्रल एक्सिस।
ओके सर, थैंक यू।
राइट जी, ओके। सो शैल आई एग्जिट क्विट? आपका सेक्शन जो है ना मुझे काफ़ी पुरस्कून सा लग रहा है। लगता है आप लोग खामोशी से आके क्लास में बैठते हैं और खामोशी से चले जाते हैं। नेक्स्ट टाइम मैं हो सकता है मैं आपको कहूँ कैमरा ऑन करें और मुझे अपने चेहरे दिखाएं कि आप कोई अटेंटिव हैं या सोए पड़े हैं सारे। चलें, अभी रमज़ान था तो हमने थोड़ा सा आपको लीनियंसी शो किया, बट लेटर ऑन आई विल मेक श्योर कि ईच वन ऑफ यू आर पार्टिसिपेटिंग इन द क्लास। ठीक है, ओके, अल्लाह हाफिज़।